interaction. Let the patient control the robot for their health care. So author is Jinhui Ouyang.
Yeah.
Okay, from Hunan University.
Yes.
Okay.
Okay.
Great.
Hello, I'm Jinhui Ouyang from Hunan University. It's my pleasure here to present our work. DeepBrain enable fine-grained brain-robot interaction through human-centered learning of coarse EEG signal from low-cost devices. DeepBrain is an edge AI system that precisely identifies brain intentions through low-cost EEG devices to realize brain-to-multi-robot interaction and then assist users' household tasks with only their brain signals. Before we introduce our system, we conduct a survey study to find out the difficulty that impaired people encounter in daily life. 2 research questions are presented to the participants, which are the challenges they face and their unwillingness factor for assistance. To find out the answer, we set up some specific questions, for example, turn off the light, take something from another place, and received 52 responses. By analyzing the responses, we discovered that 3 challenging daily tasks as shown. We then find out 69% of inconvenience in daily activities are related to position transferring and movements. Also, we invite the participants to describe their potential unwillingness to ask for help. Inappropriate use of equipment, travel matters, and psychological barriers are the major factors. In addition, major of them suffer financial burden as well. 36 of them worry about their financial situation, and only 7 of them can ensure the income that supports their lives. 50.9 of them suppose cost is one of the factors to choose the assistive help. The survey results guide us in carrying out the interaction system design. Some previous work have designed BCI system to help impaired people. This study used medical grade EEG devices to catch precise signals, and this study demonstrated the promise of using BCI to benefit people in daily tasks. In recent years, some commercial-grade EEG devices have shown the potential to act with robots. Although commercial-grade devices suffer a heavier noise interruption, they have superior use convenience compared with medical-grade devices. However, this study have not addressed the issues of multi-robot interaction and personalized EEG algorithms. So the problem is, how can we design a BCI system that controls multiple robots to assist user with just a low-cost EEG device? Meanwhile, considering the EEG personality issues, we designed our system with 3 major modules. First is the EEG signal processing module, which can augment the EEG data by deeper showcasing the temporal dependencies. Subsequently, to overcome the personalized issue with a limited resource edge system, we utilized an improved meta-learning framework to adaptively train an attention-based network brain transformer. Finally, we set a table of common codes for users to send the corresponding instruction to the robots. Before we design the exact modules, we set 4 categories of EEG data and collect data from system training. All the participants act on the relaxed brain activities, and we discovered that male had an average higher EEG intensity of about 32, while female of about 24. At the same time, the male's fluctuation was smoother. Based on the finding, we downsample the data and add Gaussian noise, then upgrade the dimension to amplify the temporal dependencies of the data. In the second module, we use an improved meta-learning framework to train the proposed brain transformer. We utilize residue structures and feed-forward network to enhance the attention mechanism. Then, we redesign the update policy of the meta-learning to reduce the computational cost. Inside this process, we treat each participant as the subject and each personal EEG dataset as a specific task. Then, in the multi-learning stage, we only initialize and update the final 2 layers, which are 2 linear layers. In the final module, the interaction module, we design a code map for multiple interaction. Specifically, each user can use their brain activities to guarantee generate the corresponding codes. These codes can be used as a label to consist a particular instruction. As shown in the right instance, it begins with a star instruction 000. After that, 1001 represents the user wants the arm robot to send something to position clockwise. Here, a bit 0 is the pulse symbol and automatically failed to give a user a short time for rest. To showcase our ideas in the real world, we established a demo that can use a code map to send instruction and control single or multiple robots. To more detail evaluate, first, we use experiment correlation metrics to calculate the inner similarity marked as self and the coarse similarity marked as coarse. The inner similarity of data are not very high, which indicates that the personalized issue across the subject. At the same time, the coarse similarity are very low, demonstrating the category setting is reasonable. After that, we utilize some other metrics to evaluate the system performance. We conduct a general use experience in quiet and noisy environment. By comparison, the DeepBrain showcases a better performance in both environments, which indicate its flexibility and particle ability. Then, to test the adaptive capacity of personalized issues, we use 4 datasets of normal mobility subjects to train in the multi-learning stage, and text with some small dataset from elder people. The results show that our system performs SOTA of all subjects, demonstrating personalized accuracy in the account of use convenience. We finally conduct some extra evaluation to demonstrate the real-world using performance. We discovered that the number of update layers and the length of input data influence the performance, which should be balanced in the particular scenarios. In the conclusion, there are still some limitations of our work, such as the simplicity of controlling robots, e.g. data privacy and security issues, and the latency in real-world applications. To further address the limitation, we use some advanced mechanisms such as semantic communication and dynamically processing EEG data from diverse devices. And we can achieve 50 seconds data with high accuracy. Some ideas are coming soon. By the way, I'm looking for a PhD position in 24 or 25 for. Thank you.
Okay, any questions? We got time for short question. And during the same time, second speaker can set up. Okay, any questions? Okay, go ahead.
Thanks for the great talk. I might be missing, how do you actually validate the model, the cross-validation? And then second question is, you mentioned the real-world context already. What does it exactly mean, the real-world experiment? And how did you conduct the study?
As for the first question, I evaluate my system in the realistic interaction and some accuracy performance. And the accuracy performance showed that our module has SOTA performance of all the data sets of self-established. And as for the realistic interaction, we have conducted a serious experiment of multiple devices controlling multiple robots in my new work. So maybe it will be coming soon to find out how can I show the performance of my model. Yeah, and the second question I didn't really understand the meaning. So can you pardon it?
Yeah. Talk after the talk, right? After the session, like, we can talk.
Okay, thank you.
So the second paper is neutral gate. It's basically use gate characteristic for health.